You think I should have read it?
Okay, I think maybe we should get started. Oh my goodness, what a pleasure. Welcome to our very first talk in our very new series called our Tenure Talk series. And you may have put it together that these are talks for faculty who have recently been granted tenure. And I am really excited to introduce Cem Tasan, who is our first tenure talker. And first of 3 this fall. Where's Rob and Jim? So please, I hope you guys got those in your calendar. And the reason, so first of all, you're going to hear about the incredible work that Cem has done in his career, tenure is about 3 things. It's about the research you've done, it's about the service, and then it's about the teaching and mentoring that you've done. And those are all part of the case. And Cem has made really kind of world-changing advances in each of those. Obviously, you won't have a chance to tell you everything today, but hopefully you'll hear a little bit about that. But the thing is that it's not just those 3 things, it's those 3 things and this person over there. And this person is a part of our community, and I think that's a really important piece of why I'm really excited about this new series, because I love our community, and I think we're an amazing community, and I love the idea that we have a reason to celebrate, right, and to get together. And what better way to do that than with a tenure talk? But also, I, as the department head, get to present these cases. And what happens there is I really get to know the case in great detail, and then share that with the dean and other department heads in the school. And I feel that has been a tremendous honor to get to know the work of my colleagues in that way. It has been actually amazing. and I stand awestruck as I go into the depths of what these people have accomplished, like Cem. And honestly, like, one of the words that comes to mind when I think about how can I describe that is just pride. Because I feel really proud to be in this department and have a colleague like Cem. So with that, I hope that you feel a little bit of that too as part of this series. And let's all welcome Professor Tasan.
All right, can everybody hear me? All right, so thanks, Jeff, for this beautiful introduction. And I'm going to explain the hats, but a bit later. So first I'm going to start with this title, actually, where this title is coming from. So the title is Metals Up Close, or Have I Stopped Worrying and Started or Loved the Tenure Track Life? This, of course, goes back to this movie. And in this talk, I will be often talking about movies, too. So it's not only about metallurgy. And this movie I've chosen for a certain reason. Kubrick in this movie is taking a very difficult topic, a possibility of Cold War, a nuclear war, a topic that's very tough and stressful and dramatic, basically. I think tenure process is a bit like this. There is the possibility of a dramatic end to this, and it can be a very difficult end, but there's also a lot of fun in it, in my opinion. And this is a comedy, actually. So this movie is a comedy, so it's fun to take a look at it. And I think it would be a nice analogy here. All right, but if we get more serious, our story starts a bit earlier. So if we are going to talk about metals, we have to go way back. And this is one of the depictions of the times when metals were already being dealt with. And in this crowd here in this little village, my favorite guy is this dude here. So if you look at that guy, he's not baking bread. He's a coppersmith. This guy is trying to make metal, and he's working in the industry. He's working in the defense industry mostly, producing helmets and swords and knives and things. And if you look for a second and think about the expectations for these materials, it's hardness and wear resistance and durability, and that's more or less it, right? So there are various limitations, obviously. Now, if you go back 4,000 years, well, it depends on where in the world you are looking, but let's say in some regions 4,000 years. So now the metallurgists have slightly different costumes, and they are using much more cooler equipment. But they are trying to deal with problems that are much more complicated. So now the expectation from metals is to not only deal with wear resistance and durability, but also deal with high temperatures, low temperatures, corrosion, high deformations, impact loads, and so forth. So although we know metals for a long time, we need more from them. And what is then the technical problem? The problem that we deal with now from a scientific perspective is that most of our understanding of the physics of metals is coming from looking at simple structures and simple models. If you look in the literature, for instance, if you want to understand hydrogen effects, most of the models would be looking at a very simple structure. If you look at some of the models of dislocation boundary interactions, they are going to be relatively simple models, which is all fine. In science, we often take a complicated problem and break it down into smaller, solvable, sub-problems. But it doesn't help us always, because we know that metal microstructures are much more complex. So here's a cartoon depiction of a given metal's microstructure. So you have surface effects, different phases, different boundaries, precipitates, texture effects, different types of atoms and elements that might be there, different types of defects. And these typically coexist together. So the simplification doesn't always give the full physical description of what's going on. So the approach of my group when I started here at MIT, now 7 years ago, is to develop in situ techniques. And the idea here is, of course, making fun movies, but not only that. It was also, the fact that we can maybe better understand this complexity in its present state without really simplifying it too much, so that we can get closer to the real physics of things. So to be more specific, we wanted to create complex boundary conditions, for example, in a scanning electron microscope. And then this also would mean that we would want to have mapping techniques that look at large areas, so large field of views, but still at high resolution, so we can see a lot of things in sufficient detail. And over the past 7 years, we've developed these techniques. So we put all kinds of different machines in the SEM, so it is a very frightening experience for me as a PI. I always hide somewhere and expect to hear the bad news that something is broken or exploding in the SEM, but that news never comes, luckily, thanks to my great researchers here. And when we do that, we can get all kinds of information about evolution of these complex microstructures, and that teaches us how to deal with this complexity. So in this talk, in the first part of this talk, we have a lot of time, so I'm going to first focus on the 3 core aspects of my research: methods, mechanisms, and materials. With methods, I mean the new techniques that we develop. With mechanisms, what I mean is once we develop these new techniques, we can better understand some of the key physical mechanisms. And with materials, once you understand key mechanisms, you can go back and design new materials, new metallic materials. But that's only the first part of the talk. And in the second part, I want to talk a little bit about how I stopped worrying. So this is more the personal side of this 10-year story. And I want to talk there a little bit about little adjustments and little pleasures. All right, so let's start with the method side. So there are a lot of things that happened here, and I'm going to focus on one group of methods that we developed, and that's going to be on a specific topic. And these were the guys who contributed to this. And mostly it's Jinwoo, Haoxie, Moadese, but Michaela Kuyungsik-Ben has also contributed to this research, and some of them are here today. So this is a paper from 1874. 1874. It's been a while since this thing was published. And if you take a look at it, this researcher, William Johnson, is basically talking about what he has observed when he put iron in contact with, essentially with hydrogen, and how he observed hydrogen embrittlement to take place. So this is 150 years ago, or more than 150 years ago. So normally in science, if we have a problem that's 150 years old, then there are solutions that are already identified. In this case, it's not really the case. Although we have solutions, it's not really fully getting rid of this problem. These are some articles you can see in the newspapers in the last decade or so, where components suddenly fail out of the sky in big towns, and component failures in bridges and so forth. And you also see probably news about new energy solutions using hydrogen and how we have a need for a new infrastructure to transfer hydrogen safely around. Now, why do we have this problem still standing? Well, because there are multiple mechanisms, multiple effects hydrogen can create in a microstructure, and these effects are taking place at challenging spatial and temporal scales. So what do I mean by that? So if you bring again the same microstructure cartoon here, what you can see is that in different materials, under different conditions, hydrogen can interact with each of these constituents in a different way. Surface effects, boundary effects, 1D defect effects, 2D defect effects, all of them are different interactions with hydrogen. And so it becomes difficult to understand what's going on. And keep in mind also that if you think about the periodic table for a second, hydrogen is on the upper left, which means that this thing is tiny. You can't even see this thing normally. There aren't even good experimental techniques to map where hydrogen is. So if we go back to movies and pick up one movie that's going to describe hydrogen research, I would pick this one. This is a Coen's movie, Oh Brother, Where Art Thou? Only with a simple change, it's going to be, oh, hydrogen, where are you? So where art thou? Because it's simply not so easy to see this thing. So for this purpose, the method section of my talk, I'm going to talk about 3 different techniques and quickly show you how these help us. Technique 1 is related with using an in situ hydrogen charging setup in a synchrotron facility, to be used in a synchrotron facility. Second one is an in situ SEM hydrogen charging setup. And the third one is an in situ SEM thermal desorption spectroscopy. All right. And we are going to, the examples I'm going to talk about specifically focus on one type of metal. It's a alpha plus beta titanium alloy. It's Ti64, the most commonly used titanium alloy. So this microstructure is, if you look at it in a simplified cartoon, it's something like this. It has alpha phase and beta phase and phase boundaries and grain boundaries and so forth, and some defects inside. But if you look at the real microstructure, it may be as complex as this. You would have lamellar regions and equax regions and certain fluctuations in the microstructure spatially. All right, so let's look at what these techniques can do for us. Remember, we can't see hydrogen so easily, and we are trying to understand where it goes and what it causes, right? So in the synchrotron, so now we go to synchrotron and charge a sample hydrogen as we are having the synchrotron beam penetrate through the sample. We can, of course, do diffraction, and this can give us a lot of information. So some of this information is shown here. So here we are, for instance, looking at one of the hydride peaks that may appear in a titanium alloy when you charge hydrogen to it. So titanium is a hydride former, so if it takes hydrogen, it's starting forming hydrides. But it's important to know when they form and where they form and so forth. So if you are doing it in synchrotron, then you can also do this in a time-resolved manner. So in other words, you can take a look at how this peak evolves as a function of time, which you can use then by doing Rietveld refinement to say something about the formation kinetics of these type of hydrides. Here, we are not seeing anything, so there is no spatially resolved map. I don't have a microstructure micrograph that shows where hydrogen is, but at least I see when hydride starts forming very accurately. And I can say more, because during diffraction, you can also look at the peaks that correspond to the 2 phases that are present, that was alpha and beta, and you look at how these peaks move or how they broaden to say something about defect density in them or lattice strains in them. And again, you can do it in a time-resolved manner. So you can then correlate formation of hydrides to these events taking place in these 2 phases. Now, specifically here, what you see is that as you charge hydrogen to Ti64, you see significant microstrains in beta that appear even before the formation of the hydrides. So you charge hydrogen, and these BCC network of hydrides is where hydrogen starts diffusing. There is no hydride yet, and once hydride starts forming, you can see that actually some of these strains are compensated or going in the other direction. And you can see that these strains are much more significant in the beta phase than the alpha phase. So although you don't see something directly, you are getting information about where hydrogen is going and transferred in the material. So that's one technique. So, but you want to learn more. Now you can switch to the in situ SEM charging setup. In the in situ SEM hydrogen charging setup, the basic idea is simple, that you have in the SEM a little reservoir that contains some hydrogen source, some electrolyte, which is limited by the sample itself. And on the other side, you have your probes. It could be mechanical probes, or it could be your electron beam. So essentially, it's a permeation test where you are charging hydrogen from the bottom, and you are looking at it from the top to understand what's happening. So if you do this, you get movies like this one here. So we are looking at Ti-64. If you look carefully, time is evolving, and you see this hydride forming at the intersection, at the phase boundary between the beta phase and the alpha phase. That's this blue region. And then you can switch to electron backscatter diffraction, EBSD, to actually analytically prove that it's the hydride phase that's forming. So the synchrotron diffraction analysis told us something that's more about a more average response. And it's a time-resolved response. And now here in the SEM, we get a spatially resolved information, which already shows, if you pay attention to this, that this effect of hydride formation is not very homogeneous. You have thicker hydrides forming in certain regions than other regions. And you can further analyze this data to learn more. One of the things that you learn, for instance, is that if you have these equiax regions, equiax beta regions, compared to these lamellar regions, you have thicker hydrides forming. And in fact, it's those thicker hydrides that contributed to failure more significantly. You can calculate defect densities by comparing EBSD measurements before and after too. So all this basically tells us, by doing this analysis in a complex-looking microstructure, what you basically learn is then that in Ti-64, it would be actually much better to have a fully lamellar microstructure rather than combination of these thin beta phases and the thicker beta phases. And the idea there is very simple. You are creating many highways for hydrogen to diffuse, so you are essentially dispersing hydrogen and effectively reducing its local effects and reducing the embrittlement. All right, so you can, in the in situ SEM charging mode, you can also learn more. So one of the effects is, one of the other dilemmas in the literature was about hydrogen's effect on dislocations. So hydrogen, it was already shown by the beautiful experiments by a transmission electron microscopy group that hydrogen can come to dislocations and basically change their spacing. But it was, these experiments were not confirmed by atomistic simulations that basically say that hydrogen essentially would decorate a dislocation, like a more conventional interstitial effect, essentially creating an atmosphere, a Cottrell atmosphere around the dislocation, limiting its motion. Rather than causing it to move, it would limit its move. So we were looking at this and thinking, maybe our in situ techniques are very capable to help us. Now, remember what I was saying before. We can look at very large regions, but we still have the right resolution to see the details. So in this case, in the SEM, you can do ECCI, electron channeling contrast imaging. Now, for instance, pay attention here to the micron bar here. So this is a half a micron, and we are looking at a region that's microns long, and we are looking at individual defects, dislocations, dancing around, as we charge hydrogen to the sample from the bottom. Now, this increases your statistics tremendously. And instead of having these data points that sort of don't correlate, you can create much more data points for this problem, which basically teaches you then that it's not just about modeling one dislocation and the hydrogen around it. You really have to take into account boundaries in this problem to be able to better understand the hydrogen effects. All right, so these were some examples of the methods that we developed and how these methods help us better understand the mechanisms and the towards design of materials. Now, in terms of mechanisms, of course, we put much more effort as we developed these new techniques. We had worked looking into mechanisms of plasticity, work that's looking into mechanisms of damage and fracture, and mechanisms of phase transformations. And today I'm going to focus on a particular mechanism that can be best represented by this particular movie. All right, so this is a movie by Tim Burton, Edward Scissorhands. And the key thing here is these hands that have these blades, these sharp blades. I'm very sad because Gianluca is not here. Otherwise, I would show this beautiful little move I had. But you can tell him later when you see him. So the idea here is looking into blades and why blades can't be better, or what is causing them to fail. So I picked this topic for this presentation because it follows the same theme, that we are looking at a material that's very well known, on which there are literally thousands of years of optimization, and a topic that you would think, we know everything that needs to be known here. And again, one of the themes of the conclusion of this part will be looking deeper, looking at metals up and close. You learn more that helps you to innovate and get to a better position. All right, so this is sort of the back, history of it literally goes back thousands of years. But if you look at the design philosophy, if you talk to people in the blade industry, basically the philosophy is very simple. Increase hardness. If you are going to make a cutting tool, increase hardness, that will increase wear resistance, and that's it. And that's basically coming from these type of correlations that's abundant in metals literature or materials literature, where wear resistance is correlated with an increase in hardness, which seems to make sense. If you make a material harder, it becomes more difficult to wear it down, so it will go longer as a cutting tool. But we know that this is not always true, right? We know that we are using these cutting tools in our daily experience, and we are cutting very soft objects, yet they get duller with time, and their operational functionality basically decrease. Now, this is a point where I would suggest, getting closer and looking at the problem a bit closer. And if you look at it closely, you start seeing that all of the blades that you see, for instance, razor blades that you see, are more or less the same type of steel. So whatever blade that you buy is typically going to be the same steel, same type of martensitic stainless steel that is rich in carbides. Because the design philosophy is, again, the same, increasing hardness, reducing wear resistance. But wear is only one possibility of failure for a sharp object. In reality, it might also be that there is plastic deformation, there is brittle fracture, or corrosion might take place. I mean, some of these tools are used in wet environments. And what Gianluca has noticed is that as you carry out these experiments and look at possibility of wear, you see that actually you can't really recognize any significant wear taking place at intervals where you would normally experience a reduction in the operation of these kind of tools. So for instance, if you take a blade and literally start shaving with it 20 times, 30 times, he would see basically no significant wear taking place if he would image the same blade over and over again. However, at the same time, he would see chips forming. And this was the interesting finding he had, that by cutting human hair with these martensitic stainless steel with, full of carbides, a very hard material, how can we actually create these chips? And we didn't believe it at first, and then we resorted to in situ experiments, and he carried out two types of in situ experiments here. And one of them is to just see the mode of deformation in the blade, and the other one is to actually measure the forces associated with cutting human hair on the blade. So these are the type of movies he developed. So here's the hair being cut, and here is the blade. And if you watch this movie over and over again, you can see that here, as we go through, this cutting just one hair actually creates these chips. Keep in mind, this is a sort of a painful shaving experiment because we are in the SEM, so it's not, you don't have any lubricant or anything. But it's the same type of mechanism that we see in the post-mortem analysis. Now, what's more interesting is you don't see it every time. You don't see these kind of chips appearing every time you make a cut. You see it only when, under certain occasions. Here you have the first cut, second cut, third cut, and you don't see any chips. And at some point, in a fourth cut, you start seeing a chip in one of those locations. So it then becomes a curious situation. There must be some conditions that need to be meeting to be able to create this kind of a failure mode, apparently. And so to be able to do these analyses, he also carried out these cutting experiments where he could measure the force on the blade, which then can be used in further analysis and simulations. Anyway, so if you look at this analysis, his summary was the following. So, all right, we have this blade. This blade is going to feel some sort of force due to the hair being hair interacting with it, and the angle of this interaction can be different. And on top of it, on the blade, there are also going to be small notches coming from the processing. The positioning of those notches will also be different depending on where the hair is interacting. And basically, looking at this, he came to these two critical plots. The first plot is essentially telling us that it is indeed very important that if you have a blade, the angle of approach is really important. So if you look at my hand and think of this as the blade, if the force that is applied by the hair is sort of inwards, sort of pushing the blade back into itself, then the situation is not that critical. The stresses don't rise so much. But if you are actually putting it, if the hair is pushing the material out of plane, then it's creating this more dangerous mode, which is increasing the stresses around these notches. And he's also noticed that if you think of my hand as the blade, and if you think of this opening as the notch here, it's very important where the hair is hitting. If the hair is sitting exactly on the notch, or if the hair is sitting very far away, it's not that critical. But apparently, if the hair is really hitting just next to the notch, it becomes the most critical situation. And further, he's also realized that one of the most critical aspects is having a heterogeneity in the material. If you have this notch between a compliant region and a soft region, it actually becomes much more likely that you'll find regions where crack growth is going to take place. So what is the conclusion of this? The conclusion of this study was, yes, high hardness is good for sure, but we need it in a uniform way. Otherwise, we have this crack growth situations. And you might say, well, why is a Martenstick stainless steel, this optimized material for decades, not uniform? Well, from an engineering perspective, it looks uniform, but as you zoom into it, and as you start thinking about the scales that are involved, you quickly realize it's not actually that uniform. As you make a blade out of a material, of course, at the tip of that blade, you are selectively choosing some microstructural features to be there alone. So here is one example, for instance, one cross-section that Gianluca produced, which had a carbide at the tip of this blade, which is has a very different local behavior than other Martenstick regions, Lath Martenstick regions. And even without the carbides, actually, it's been shown that martensite can have a lot of heterogeneity in its structure. So we learn a lot from these in situ insights, and what's then next is to ask ourselves, well, now that we learn these mechanisms, can we do better? And the guidelines we got here is that, okay, we need chipping resistance, and that seems to relate to homogeneity. We need to, of course, keep hardness very high. And I haven't talked about it here, but we also need to get rid of carbides for corrosion resistance. So what Gianluca is now working on in a startup is to come up with a technology that sort of uses this kind of insights to make blades in a very different way. So what he's proposing is using tapered rolling technology, where you have a number of rolls here, tapered in such a way that as you pass the material through these rolls, you are essentially creating a number of blades, actually two on either side. And he was already, I'll go a little bit faster here, he was already progressing with this and actually attending bladesmithing contests in the TMS and so forth. And he repeated some of these experiments that he's carried out with conventional blades and demonstrated that when you have this kind of idea where you produce a lot of deformation, so you create more homogeneous hardness and higher hardness, then you can actually cut hair to tens of times. And this movie goes on, I think, to 24 or something, and you don't see any chip formation here. All right, so the second part of my talk was about these mechanisms. Again, the theme there was looking into using these kind of in situ techniques to understand how these mechanisms, what critical mechanisms are, and how we can deal with them to make better materials. Now, the third part of my talk is going to focus on materials, and you see, again, a number of my group members contributed to this research. So actually, this is a little bit related with a question Professor Xu asked me. So Chris asked me when I was in the first presentation here at MIT. I wasn't working here yet. I was interviewing, so I gave a talk about what I plan to do. And I showed some trip effect, and I don't know, Chris, if you remember this, but Chris asked, you know, is there nothing new in this trip thing? It's been the same thing in this field for like decades, something like that, Chris. And I think I dodged the question in some way, and, but it was fine. But it was a topic that was on my mind for a while, right? The problem here is the following. We want Martin-stick transformation because it gives us many various benefits. We get trip effect, we get toughening effect, we get ductility. For instance, having deformation-induced Martin-stick transformation increases strain hardening rate, and that gives us essentially increases in both strength and ductility. You can make materials that are both strong and ductile. However, this kind of transformation also has some disadvantages. As a result of this transformation, you are introducing also a phase that is a little bit prone to damage and failure. So martensite that is introduced is actually a typical damage site when you further deform this material. So it's a funny situation a bit. You want a transformation, but you don't necessarily want the end product or something like this. And you can see this in this nice movie in Shalu's research, where you are deforming a material and you get this nice strain hardening response, but that's quickly followed by damage nucleation at this boundary because of the Martin-stick transformation taking place. So it's a strange situation. You want the transformation, you want the end product, but it's also the end of the material in a way by causing damage upon further deformation. So how do we solve this? How do we still have the benefits of the transformation, but get rid of the problems that it's generating? Now, the movie that I can connect to here is a movie by Woody Allen. It's called Zelig. So Zelig is a story of a guy who enters different environments and can transform. So if he's meeting with geologists, he talks like a geologist. If he's meeting with metallurgists, he talks like a metallurgist. If he's talking with gardeners, he talks like a gardener. So it's this guy who can transform very easily. So following that kind of idea, I'm going to quickly show you 3 solutions that we spent time on and demonstrated to be possible. One of them is thermally induced reverse transformation. The second one is reverse transformation upon unloading. The third one is mechanically induced sequential transformation. Now, remember the problem we have for a second again. We have this transformation, we have this mechanically induced phase transformation, we want that transformation, but we don't necessarily want the end product, so we want to find ways of solving this. And these 3 approaches all try to treat this problem, but in slightly different ways. Let's take a look at them one by one. So in case of thermally induced reverse transformation, as the name implies, what you are doing is you are designing a microstructure that is designed in such a way that you can have the forward transformation that you want. So you deform it, there is going to be the forward transformation. But then you can apply a heat treatment. Because you design the microstructure in a certain way, the material comes back to a state that's very similar to what it began with. So essentially, you are applying a heat treatment to revert the microstructure back to its original state. So if you do this, so it looks like this, for instance. You start with a BCT FCC microstructure. This specific example is a medium manganese steel. You deform it 8%, so now the Martin-stick transformation has taken place. So you only see the BCT at this point. And then you apply a heat treatment, and you get to a microstructure that really resembles the beginning microstructure. So here, one might say, well, in metals, we can always do recrystallization. So what's the big news here? The news is related with how close you can get to your starting microstructure. It's actually not that easy to come back to your starting microstructure if you take a random material and deform it and then try to recrystallize it. Now, the nice demonstration of this is actually by mechanical testing. So this test was kind of interesting. So you take a material here, you take this material, you deform it to 10%, you record your stress strain curve, then you take it off the clamp, do a heat treatment, do this treatment, come back, and repeat the same test. And basically, you get the same type of mechanical response, the same mechanical response. And then you stop at 10% again, do the heat treatment again, and you get the same response. So it's basically 3 curves on top of each other, which demonstrates that the material can go back really to a state of a very similar state to the starting microstructure. So why does this work? This works because the transformation that is taking place forward and backward here is really governed by, is really controlled by local segregation of alloying elements. In this case, we are using manganese segregation cleverly to be able to control where martensitic transformation is going to take place, and then reverse austenitic transformation is going to take place. So the key here is the design of this microstructure that's going to give this chemical heterogeneity that gives us the benefits. So that's the first approach. We are doing a heat treatment to get the microstructure back to its original state. Now you can see that it works, but it's, the key is elemental segregation, but you also see the problems it has, I think. How many applications can you think of where you can take a component out of service and put it in a heat treatment and then bring it back to service? That's not really very possible for all kinds of reasons, feasibility, oxidation, and other things. So the second approach solves this problem. So in the second approach, what we are looking at is a reverse transformation upon unloading. So this is a very different idea which is schematically shown here. So we are going to create a microstructure. This microstructure has the metastable phase again. So that phase is going to transform again. But now when we release the load, that phase is going to have a reverse transformation back to its original state, original crystal structure, original phase, I should say. So you can imagine that this doesn't really make too much sense in an example of quasi-static loading. So if you are constantly loading a material, this wouldn't take place. But this kind of concept is more for fatigue scenarios, where you have cyclic loads that would open, that would create stresses at the crack tip and release of stresses upon tension and, for instance, compression cycles. So when you have stress, then you have the forward transformation. When you have downtime, you have sort of the reverse transformation taking place. So it's nice to make these cartoons, but can we actually make this kind of material? So this is a titanium nickel vanadium alloy that has this kind of microstructure. So titanium nickel is the most commonly known, or most well-known and most commonly used shape memory alloy and also superelastic material. And what we really want to have here is a second phase that we can introduce in the material, which is essentially showing some superelasticity, where you could, with further forward deformation, you'll have the forward transformation. With first deformation, you will have the forward transformation, and as you release the load, it's going to, by itself, transform back. So we tried to create this titanium nickel nanoprecipitates, which was successful in vanadium titanium nickel system. But how do you even prove that it works? It's not so easy, actually, to show these transformations. First attempt, you can go to a synchrotron. We talked about in situ measurements in a synchrotron, and you can do a deformation experiment. Here in the y-axis you have stress, x-axis you have strain, and you are looking at certain peaks that are going to represent this kind of transformation. So you load, unload, load, unload. You want to see the forward signs of the transformation taking place and the reverse transformation taking place. All right, so we load it. So we go from 0 to 1. And if you look at these couple of peaks, you can see new peaks forming. And then we unload. So you go from 1 to 2. You release the stress, and you see that some of those peaks are disappearing. And you can repeat this multiple times. It seems to work. That's nice. But if you get a little bit too ambitious and deform it too much, it doesn't work anymore. So if you deform it too much, now you have the forward transformation. If you unload, it doesn't fully go back to its original state. So yes, this kind of mechanism seemed to work, but it's actually only a certain deformation regime where it sort of works. And I'm also a little bit cheating here, because the sample that we've taken to this facility doesn't only have the small titanium nickel features, but also have coarser titanium nickel features. So actually looking at the synchrotron measurements, we are not fully sure whether you have the forward transformation and back transformation taking place. So the only other solution you can do is go to a transmission electron microscope and actually carry out an in situ deformation experiment, where you do carry out selected area diffraction on each individual titanium nickel features that you can find. And by doing that, we've demonstrated that, again, you can have the forward transformation. So this is from B2 to B19 prime, and then reverse transformation, although this reverse transformation in this case didn't fully take place. Right, so the second solution to our problem is having the reverse transformation when you unload. And this seems to work, but again, we have the key idea here is alloy design, so that you can have this phase that exhibits this behavior. The concern, of course, is that you can create this kind of behavior only in a narrow range of alloys. You need to be able to introduce a superelastic second phase in the right dimensions, in the right phase, to be able to have benefits of this. So maybe not too good of a solution. The third idea is mechanically induced sequential transformation. And here, let's go back to our problem again. Our problem was we want the forward transformation. We don't necessarily want the end product. So maybe you can think about systems, you can design systems where you have the forward transformation, and then you have another transformation taking place. So you create a sequential transformation mode. And this is Shaldo's work that showed that this is essentially something like a dual trip effect, right? Double transformation induced plasticity effect. So instead of having the cracks here, we would have a second phase that is introduced, and this would perhaps bring additional strain hardening and so forth. And Shaldo has demonstrated this by carrying out in situ experiments again. Keep in mind, these, again, very complex microstructures, very fine details, so we have to look at things as they happen. And here, again, these in situ techniques become very important. And what is demonstrated here for this particular alloy, iron, manganese, cobalt, chromium system, is that as you deform this FCC system, you will first have the HCP martensite form. And as you further deform, you see some surface features appearing. And by further analysis, diffraction analysis, EBST basically, you can identify that this is a newly formed FCC phase. So you have FCC to HCP transformation, and then further deformation leads to HCP to FCC transformation. But keep in mind, we are very deep into the plastic regime here. So we are not looking into elasticity. This is not superelastic effect. We are talking about a newly formed, a new FCC here. And the key point about this new transformation, this is a very busy graph, but I wanted to share with you anyway, because you can form a new phase, but if that phase is not deforming or that transformation is not accommodating strain, maybe that's not so useful for you. And this plot essentially shows that when you plot average strains to local strains, this region that exhibits the double transformation both accommodates strain during the transformation, but also during the further deformation. All right, so if we take a step back again, what was the idea here for this third solution? That is that you would design a microstructure that would now show two transformations. And these kind of transformations would perhaps delay damage nucleation to higher strain. So you make a better material, essentially. So it seems like this idea also works. The key here is the availability of transformation pathways. So not every crystal, you can't go from every crystal structure to another, so you need to have a transformation pathway to realize it, which also, of course, creates a limitation in the range of alloys that you can design for this purpose. So 3 approaches. So to the answer to the question Chris asked, none of them are perfect. They all have limitations, but that's life, how engineering life is. You always come up with solutions that can solve parts of problems, and hopefully, by further optimization, you can enlarge the regime in which these kind of solutions work. All right, so that's about metals up close. So as I talked about these 3 groups of activities, methods, mechanisms, and materials, the theme was always the same, and I intentionally picked up problems that are very conventional, like Ti-6-4, martensitic stainless steels, martensitic transformation, very old topics. And I hope that I could show you that by using new tools and detailed analysis being up and close, we can learn much more about even these very basic materials to push our engineering solutions further. So what's the future from a technical perspective? Well, the challenges remain, right? We still want, obviously, 7 years didn't change the global picture here. We still want metals to do more. What is becoming very clear is the availability of advanced processing solutions. Here's just one cartoon, but there are many advanced processing solutions, some of them under the umbrella of additive manufacturing. So this basically means that the future will have more opportunities to mix things up. So instead of having homogeneous microstructures, we'll be able to perhaps have gradients of different sorts. And the type of tools that we have that combine large field of view and detailed insights actually are perfect for providing guidelines to these newly emerging fields as well. All right, so that's the end of the sort of technical part, and now comes the sort of more personal part. So this was a long journey for me, and I also wanted to share a little bit about personal sides of this journey. So, once I came up with the title, How I Stopped Worrying, I had to actually ask myself, did I actually stop worrying? I wasn't sure whether the answer was yes, but then when I thought a bit, in the last year, okay, let's not talk about the last year, but before that, there was a point, third year, fourth year, fifth year, my worry significantly reduced. And this is not because, any arrogant feeling of any sort, but rather I felt that things were going the way they were supposed to be going. And then I said, well, in this talk, maybe I can go back to that time and think about and what actually caused things to feel better and what caused things to go better, because maybe this information can be more useful for people who's going to have this kind of journey. And I decided to call this, little adjustments and little pleasures, because the big adjustments I think everybody knows, but maybe these little adjustments are more easy to do and more useful for everybody. All right, so little adjustments that helped me and that perhaps may help others that's going to start a journey like this. So starting is about research ideas. So this room is full of very clever, very smart people, and we all have very good ideas. But I think that can be a little bit, that might not be ideal at certain times. When you have a good idea and you are convinced by it, it takes an effort to look at it from outside a bit. And that's why I think my first little adjustment that I would suggest for others who's going to have a journey like this is listening to the field very carefully and hearing what they say. Field meaning, your own research field, perhaps. But also, not only people dealing with fundamental research, but also people who are in engineering. Listening to industry and listening to people who deal with this kind of problem day to day is very revealing in terms of where your solutions actually sit, whether they are useful solutions or maybe they are or not. And it helps you reduce the amount of effort you need to put in certain activities. Now, the second little adjustment is related with supervision. So you can be the best scientist in the world, but you still have to work with people and you have to supervise people, mentor people, and your success and your achievements also depend on how they function, basically. And here, two little adjustments I want to share. One of them is the fact that you have to accept that one size doesn't fit all in terms of mentoring, right? At MIT, we get a bunch of very clever, very hardworking, very ambitious students, but they all need different things. They all have different expectations. They all need support in a slightly different way. And as a supervisor, the more I realized in myself that the more I tried to apply the same techniques, the less it was successful. And the more I paid attention to the researchers' individual characteristics and needs, the more things worked to everyone's favor. And then the second one is following Phil Jackson's strategy. So here I would have preferred to have, I don't know, Noam Chomsky or Nietzsche or something, but instead we have a basketball coach. So Phil Jackson, as some of you probably know, is the celebrated coach of Chicago Bulls and Los Angeles Lakers. So he had to coach players like all-time greats like Michael Jordan and Kobe Bryant. And in one of his books, he's mentioning this challenge, which is not so easy, right? These are perhaps the best basketball players ever that existed. But it's not so easy to have them do the right thing because they also have big egos and things like that. And one of the suggestions he had, which was, I think, very influential, is telling them to wait for the game to come to them rather than pushing themselves into the game too aggressively. That would basically mean not trying too hard, but rather letting the game come to themselves. So it's a bit, I think it's a very clever strategy. So also with the researcher mentoring, what I've noticed is that the more you try to, with any given researcher, the more one as a mentor tries to enforce certain ideas in certain directions, it actually sometimes decreases the chance of success for that researcher. And it's very important to look at what the researcher is needing and provide the corresponding support based on those needs. Now, the third little adjustment I did was looking related with funding, and this is a big stress for many people in a tenure track process. And the first one, I think, again, this repetition of the previous one, which is listening to industry carefully. And this was perhaps the most beneficial thing that happened to me in my career here at MIT. Listening to industry carefully is very important, even if there's not going to be a funding flow, because it's a very effective way of learning the most critical problems, which somewhere in the funding scheme will enable you to get some support if you orient your research directions accordingly. And many of when I talk to people at the same stages of their careers as me, often you hear that industry research can be boring, or some research can be boring, and even though there is funding there, it might be boring. What I've noticed is that many topics that seem at first to be boring, you realize with time that there are many interesting things in them. So one needs to be, I think, a little bit careful before really limiting their options to few funding resources. And in the end, I wanted to keep this one in also. It's also about the hours, and it's the hours that one puts in. I don't know anybody who's going ahead in life in situations like this that doesn't put the number of hours that are required for this. And I specifically wanted to include this in this little presentation, because sometimes we are at MIT and everybody works a lot, and it sometimes is almost a cooler thing to mention that you don't work so much or so. But I wanted to say that I worked a lot for this, and I think it is a need, working a lot. If you want to solve the critical problems, I think this is a need, and it's a good thing. It's not a bad thing. But of course, getting help where needed is also needed. All right, so that's about the little adjustment I did, and hopefully that's helpful to some of you. And I want to also add in the end little pleasures. So the final movie I want to show is The Good, the Bad, and the Ugly. Of course, many of you, I think, know this one. So any journey will include ugly parts and bad parts and also the good parts. We won't talk much about the ugly parts here, but I can mention some of the bad parts. So the journey here was difficult because many bad things also happened. For example, my father passed away, a few years ago when I was here. My father was in Turkey. My connection with my family decreased because of the distance that is involved. And other similar challenges, personal challenges that we don't always talk about. And these are parts of life, as well as these ugly things that may happen to one. And I think it's important to mention that they exist, and because that helps us, that helps one position oneself when one goes into a journey like this. I won't say more about the bad things, but maybe tell a little bit about the good things. And when I think about these good things, the little pleasures, I remember yesterday I was thinking about them, and I remembered all these funny moments throughout this journey. It actually already starts on the day of the interview. I don't know, Chris, if you remember this. This story involves you. So the interview here for a tenure track professor involves meeting in the morning first with the department head, and in that case, it was Chris. So we met at the entrance of a hotel, and we went to the breakfast place there. And I was then living in Germany, so I wasn't too used to sort of quick American English, native English, obviously in conferences and things, but not too much. And the lady the waitress arrived and asked us what we want to eat. And I'm meeting with my potential future boss. I'm trying to be this nice guy, and I picked something very quickly. And so in the end, what happened was Chris got this one plate that's just basically empty with, I think, like one avocado slice or something. And I got this gigantic, pan of pancakes with Nutella just pouring off it. I know, you would like this one. So I thought, okay, this job is gone already, you know. So it's not even possible to eat it. So I think like midway I had Nutella on my eye, and it was just a bad start. So anyway, that interview went fine, and I came back home, and Jeff, I think, was then the chair of the search committee or something like that. At least he was the one who was interacting with me. So Jeff sent me an email that said, everybody told me that I shouldn't send emails to check the status of my application. But I did. I sent an email to Jeff. I said, you know, Jeff, what's going on? You know, when is that? In a polite way, I asked, you know, is there an update? And Jeff sent this famous sentence now, Cem, you surely made a lot of friends here. We will be in touch with you soon. I think this email is read by like 100 people. I took it to every person I know, saying, what does this mean? Do you think it's good? Some people are saying, no, it can't be good. You know, why is he saying this? And like, I think I waited like 2 more weeks or something, and then sent another email. Then Jeff sent another annoying email like this one. Anyway, but the story has, of course, a happy end. And that happy end is the phone call from Chris, which is one of the really special moments in my life. But then it wasn't the end of the funny moments. So I started working here. So I'm a metallurgist. I need to my group needs to prepare samples. So when you talk with bosses, future bosses, you can't really be too demanding, right? You say, oh, everything is fine. But once you start working, you really have to look into sort of the conditions in the field. So I started working here, and I went to the metallurgy lab. And man, I should have taken a photo. Like any object you can think of right now was in that lab at that moment. Anything you can think of, oranges, you know. This is before Seamus's time, before you arrived. And it's true, right? Like oranges, carts, and bottles, and like everything except metallurgy tools, basically. Like everything else except metallurgy tools. So luckily that improved. I mean, Seamus's arrival changed things significantly. And then the next one is about keeping researchers happy. So I have a wonderful group of researchers, but they work so hard, and I always want to find ways of keeping them happy. And one idea was, after the first promotion, taking them to a ski trip. And some of you will remember this. So the idea was that we would go and come back as a happy group. We went as a happy group, but we came back with 4 crutches, basically. So apparently everybody knew skiing already pretty well, but not that well. So they disappeared once we got there, but then they came back with crutches, and that wasn't ideal. So after this promotion, we had just like a milk drinking celebration or something, no skiing anymore. And finally, I wanted to add this, of course, the final phone call from Jeff about the tenure, which was also a nice moment. I think moments like this should be really remembered. Otherwise, one starts remembering only the bad things or the ugly things, and one gets one misses the fun stuff, really. Anyway, so I'm finishing here, almost on time, which surprised me. So I want to thank, of course, all my colleagues. And this is not just a random statement. In some ways, I think this journey can't be shared with, to a full extent, I feel that it's only the colleagues that can understand the nature of this journey. It's only them who actually went through this and who understand the complex feelings that go through with it. This ambition, at the same time, the hard work and the sacrifices and so forth. So I'm very lucky to be working with such a wonderful group of colleagues. But I want to specifically mention 3 of them here, so to embarrass them a little bit. So start with this Elsa here in the final run. So the rule in our department is, you need to know just one rule in our department. If you have a problem, you go to Mike Tarkanian or Elsa Olivetti. That's the rule in our department. So thank you, Elsa, so much especially for that final run. So Chris is very tough, has been very tough with me, I think, but that's what's needed. So I very much appreciate all that hard work. Even when I felt that things were going well, meeting with Chris was always like a punch, so that I would go back saying, okay, I need to go back to the drawing board. And when things became really difficult, also, Chris's help was very, very influential. So thank you very much, Chris. And obviously, Jeff, not only in the final run, but also in, during all these complicated things happening, Jeff's help was so critical. So I think you spent probably more time in my narrative than I did, so thank you so much for that too. Some of my colleagues deserve a little bit more special attention. So here is Jen, here is Raf, and here is Julia. So I couldn't find a photo with the four of us. There's one photo, but we couldn't dig it so far. So we started at the same time, and this journey actually would have been much less fun, much less fun if it was a journey alone. So Raf is here representing this quartet, I guess. Jen is already gone to, across the pond. Unfortunately, we hear news about Julia as well. But I want to thank all of you for joining me in this ride and having holidays together, and our kids are growing together, and thank you very much for that, Raf. And of course, my group. So these are photos we took at the same place in the Harvard Bridge every year. So all of my group members should be there. Without their work, none of this achievement can be achieved. And so I want to thank each of you a lot for that. And here's my family, the bigger family here. And this is the point where I explain the hats. So this is the ceremony where my sister, so this is Dora, who's also sitting here, my daughter. So this is my sister, Tunam. So she is a professor in University of Amsterdam. And this ceremony was for her to, get to this full professor promotion. And in that ceremony, we were in this 400-year-old, church, and everybody was wearing, dresses and fancy hats and everything. And I was complaining to Elsa all the time that, why don't we have things like this? We need the ceremonies, we need funny hats and things like that. And you see, I got my funny hats. So now I'm a happy, now I'm a happy person. And of course, this is the closest family. So Seçkin is here, my wife, and Dora, my daughter. This is a photo we took just after Jeff's phone call. So Jeff called me to say that I got tenure. So I went home, opened a bottle of champagne, I think. We had it. And then I corrected some papers or something. I'm joking. No, we had fun. We had a nice dinner, and it was fun. All right, that's the end of my talk. Thank you very much for your attention.
Are you going to have waffles for dinner?
Yes.